to deal with sequence, okay, RNA obviously is a common choice, but when the sequence gets long, okay, CNN actually is also a good choice, okay, as I will show you later in this chapter, okay. This is the first scenario. The batter hit the ball, okay, the outfielder, okay, so immediately starts running, okay, so he's going to anticipate, okay, the ball's trajectory, okay, so I mean, he's going to track it and and change his speed, okay, accordingly, and then able to catch the ball, okay. So I think a lot of us is able to do that, but of course we are not professional baseball player, but predicting the future, okay, is something we do all the time, okay. Of course, I'm not saying like a long-term prediction or like the prediction here I'm talking about is probably I should use another word like anticipation, okay, anticipation, okay. So, for example, when you are finishing your friend's sentence, when you have a very close friend, when he or she is talking about something, okay, you are able to finish his or her sentences. This happens a lot of time, right? Or okay, this is all. This is also happen very commonly. Okay, anticipating the smell of coffee at breakfast. This one, okay, perhaps like this is a good example for Western people, okay, because Western people like drink coffee every morning, okay. I do know like a lot of us like drink coffee in the morning as well, okay. So you may experience something like that, but let me use another example which is much more common for for us, okay. For example, like when you see a picture of plum, you start have like a mouth water running, right? 望梅止渴. Okay, when you see a picture of a plum, then you feel like you have mouth water. Okay, this is like very common. Okay, why is that? Why is that? I mean, so this is the kind of like anticipation, because when your brain, okay, feel like it is something's going to happen, it tells your body to react in advance, because plum is sour, right? So you need more mouth water to go with that, So anyway, just want you guys to understand, okay, the prediction that I'm talking about is not necessary like okay, you are able to predict like stock price is going to go up or go down, okay, or like okay, there's like a earthquake, like we had earthquake last night, right? I mean, I'm not sure if maybe some of you didn't feel it, because it's for people in Taoyuan it's not really a large earthquake anyway. But yeah, I mean, it's still now like it's very difficult to predict the earthquake. We know that, right? So basically, okay. So the prediction here, I'm talking about. Here is not about those like a big thing. I'm talking about like a little small thing, and a much shorter period of time prediction. Okay, so maybe not using the prediction, but using like anticipation is probably a better word here. But you get the idea. Okay, so we do that all the time. So in this chapter we'll discuss recurrent neural network. Okay, so this is a class of the network that can predict the future, okay, at least up to a certain point, okay, and they can analyze time series data, okay, including stock price, tell you when to buy or sell, okay. Actually, my student, the student in my lab did like research, like this type of research, and at least according to analysis, I mean simulations, we are able to make big money using the system, but well, I never use it. Because I'm not a big fan of the stock, but yeah, because those two students who did that topic, they actually work for like an investment company, okay? So I'm not sure like if they are going to use those system in their company or not. That one I'm not sure, okay? But anyway, okay, so in autonomous driving system, okay, this type of, they can anticipate the car trajectories and help avoid accident. This is one of the active research project in my lab, okay? We are still doing that, okay? Of course, like, it is not necessary like just RNN nowadays, okay? If you want to, get a better result of that, okay? It is actually one of the toughest like problem, okay? More generally, they can work on sequences of arbitrary length, okay, rather than on fixed size inputs, okay? So all the network that we have considered, okay, so far, expect fixed size of the input, okay? Unless you are talking about fully convolutional network, okay? Yeah, for different size of input, the fully convolutional network is able to deal with that, but not as convenient, not as like powerful as like RNN, as you will see later, okay? So for example, they can take sentences, documents, or audio samples as input, making them extremely useful for natural language processing application, okay? Such as automatic translation or speech to text, okay? But for that, okay, RNN could be used for NLP application, but it is actually covered in a different chapter. As I said, I'm not going to cover that chapter, but once you learn the material in this chapter, you are more than welcome to check out that chapter by yourself, or you can take Professor Cai Zhonghan's class, okay? He has an NLP class, I think this semester, right? Okay. So he offers this class every year. What's going on? Okay. So to be exact, okay, what we are going to talk about, okay, in this chapter, we will first look at the fundamental concepts, okay, for RNN and how to train RNN using backpropagation through time, okay. You guys know backpropagation already, but what is backpropagation through time? Okay, this is a new thing, okay. Then we will use the RNN to forecast time series, okay. I will show you an example of that, okay. After that, we will explore some difficulties, okay, that you will encounter when designing RNN. The first one is unstable gradients, okay. We talked about unstable gradients previously already, okay, but okay, RNN has its own unstable gradient problem, okay, because like the previous approach, okay, that we covered in the previous, in chapter 11, okay, for example, such as dropout or like batch normalization, unfortunately, do not work well for RNN. Okay, so we will have to talk about recurrent dropout and the recurrent layer normalization, Okay, they are sort of replacements of those things. Okay, but they of course are, only work for the RNN network. Okay, and also okay, RNN sometimes have this short-term memory problem. This is especially the case when your sequence is long. Okay, so how to fix that? Okay, there are different type of neurons you could use. Okay, to alleviate this problem. I'm not saying you can completely get rid of this problem, but at a large degree, okay, alleviate this problem. Okay, two of the most famous recurrent neurons are LSTM and the GRU. Okay, so we are going to talk about all this in this chapter. We are also going to, talk about how to use CNN to handle the sequential data. Okay, for small sequences, okay, RNN can get the job done very well, but for very, very long sequence, for example, like such as audio sequence, okay, then actually CNN actually works better. Okay, so there's a particular type of CNN that is like proposed by what's that company's name? The company that designed AlphaGo. What's the name of the company? DeepMind, yeah. So this WaveNet, okay, is used to deal with particularly long sequence data. Okay, so they designed this one as well. So the DeepMind is not. They actually made a lot of contributions to deep learning. Okay, not only AlphaGo, but also WaveNet, and unfortunately we will not have time to talk about that. But they actually, AlphaGo actually use a lot of like reinforcement learning, and they pretty much revolutionized the reinforcement learning. Okay, this company. So this company is actually like has a lot of like very important contribution to deep learning. But unfortunately we don't have time to talk about reinforcement learning this semester. Okay, so in chapter 16 we will continue to explore RNN and see how to use them for NLP. Okay, along with more recent architecture based on attention mechanism. But as I say, chapter 16, we will not cover chapter 16, unfortunately. Okay, I leave this sentence here is just because like sometimes when this class, when the deep learning class happen to become like 2 semesters, then I will have time to talk about that. Yeah. So anyway, okay, so up to now, okay, all the neural network we have seen, okay, are pretty much feed-forward neural networks. Okay, this include MLP as well as the CNN. They are pretty much feed-forward neural network. Okay, the activation flow only in one direction. It goes from the the input layer all the way to the output layer. Okay, so there are some exceptions, okay, in Appendix E, but we didn't talk about Appendix E anyway, so you don't need to worry about that. Okay, so a recurrent neural network, okay, it's going to be, very different. Okay, it looks like a feed-forward neural network, except it also has a connection pointing backward. So it has a connection that points back to itself. So it's kind of like a feedback mechanism. Okay, feedback mechanism. Okay, so let's look at the simplest possible RNN composed of only one recurrent neuron. Okay, it receives input, produces output, and sending the same output back to itself. So this one. So you can see this is a recurrent neuron. X is the input, and it do some computation, and it will output y. But at the same time, it will, feed back the output y, okay, back to itself. So it is going to use x and this input, this feedback, both of this input and the feedback as the input of this neuron. So you may ask, like, how does it happen? This is actually happened in time step. Okay, time step. We call each of these as a frame. So this t minus 3, you can treat this t minus 3 as different time frame. Okay, so you can see at the time, for example, at the time t minus 3, okay, you have the input x t minus 3, and you get the feedback from the previous output, okay, and then you do the computation, and then you have this output yt minus 3, and this yt minus 3 will be feedback to the time step t minus 2, okay, to be the input of the same neuron, Okay, the reason we draw like this is like we try to expand in the time dimension. Okay, all this represent just this neuron. Okay, but if you do not expand, what happens with different time step? You probably do not understand. Okay, every time this feedback is not going to be used at the same time step. It is going to be used, okay, at the next time step. Okay, something like this. So you may wonder, well, how about at the very beginning? Okay, when this neural network start functioning, what happened? I mean, you obviously you don't have you don't have feedback from the previous time step because that's the first time step, right? So you will just consider this feedback input to be 0. Okay? So this is like what's going to happen. We call this expanding, like in the time dimension as unrolled through time. Okay? So if you see this, you get an idea that, okay, actually this neuron is capable of handling like an input of arbitrary size, right? Obviously, because, well, because we consider the time dimension. So, if you have multiple input, you just feed that, input to this exact same neuron at a different time step, and it is able to take, as many, input like stuff as you want. Okay, so that is why RNN is considered like it can take like arbitrary input size. Okay, so as for the output of the single recurrent neuron for single instance, okay, you can easily create a layer of recurrent neurons, right? So at each time step t, every neuron receives both the input vector xt and the output vector from the previous time step y t minus 1. So it's going to be something like this. This is a layer of recurrent neurons. So you can see it is going to it gets the input. This x is a vector. Okay, it gets the input vector x, and it will output a vector y, and this vector y, okay, in the previous time step will be feed back to the current time step as the input again. Okay, so if you can also do like unroll through time, okay, and get idea like this. Okay, so each recurrent neuron has two sets of weights. Okay, one for the input xt, and the other for the output of the previous time step yt minus 1. So we call this weights vector, okay, wx and wy. So if you write it into formula, okay, it's going to be something like that. Yt is the result of xt, okay, transpose times wx. Okay, so this is like a weighted sum of the current input plus weighted sum of the feedback. Okay, weighted sum of the feedback. Okay, plus a bias, of course. And then after you add all this, you have to go through an activation function. Okay, this activation function, okay, it could be rerule, it could be hypertension. To be, by the way, hypertension is used very often in RNN network. Okay, to a point that RNN treat the hypertension as a default activation function. Okay, but of course, if you want, you can still use the rerule. Okay, if you want. Okay, I just want to point out that the activation function, okay, in RNN is mostly rerule. Okay, a lot of time. Okay, but obviously rerule has its own issue, as I have mentioned earlier. Okay, but we know how to deal with that, right? So, so if you have like the whole set of like neurons, okay, then because it becomes a matrix, right? It becomes a matrix. So it's going to be something like this, okay, in the matrix format. So in the matrix format, you can even abbreviate it like this, where this W is of this format. Okay, if basically this one times this one is this one. This is obvious, right? Okay, so this is when you have a mini batch. Okay, if you only have a vector, then it's going to be it's represented like this. But if you have a whole batch, then it's a little bit more complicated. It's going to be a matrix format, and this basically talk about like the dimension of all of each of these metrics. But I think this are obvious. You can easily check it out. So yt is a function of xt and the yt minus 1. And the yt minus 1 is a function of xt minus 1 and the yt minus 2. And the yt minus 2 is a function of xt minus 2 and the yt minus 3, and so on. So you can expand this all the way until what? Until time step 0, where x0, there's no y, negative 1. Okay, as I say, y negative 1 basically is a zero, just a zero vector. Okay, so you can see that once you expand this, okay, you will understand that yt is dependent not only to the current input, but also all the previous input. Okay, so x0, x1, x2 is up to xt. So yt is dependent to all these. Okay, so this is why, okay, we consider this neural network as a memory. Okay, because it sort of have a way to make use of the input of the very beginning. Okay, so so it has some certain, you can consider it a certain type of memory. Okay, and many researchers prefer to use hyperbolic tangent, as I said. Okay, activation function rather than ReLU, but the ReLU based are also possible. Okay, so since the output of recurrent neuron at time step t is a function of all the input from the previous time steps, so you could say it has a form of memory, as I said. Okay, a part of neural network that preserves some state across time steps is called a memory cell. Okay, so a single recurrent neuron, okay, is a very basic cell. Okay, later on, okay, in this chapter, we are going to talk about more complex and more powerful memory cell. Okay, which are actually LSTM and the GRU. Okay. This actually this type of neuron, okay, the complicated neuron architecture is still actively researched, even for now. Okay, so in general, cell state at time step t actually can be denoted as HT. This is a state of a neuron. Okay, H stands for the hidden. Okay, so because it's a hidden state. Okay, so this is a function of some input at that time step and its state at the previous time step. So its HT is going to be the function of HT minus 1 and XT. So you feel like, well, this looks just like a YT, right? Sort of, yes. Okay. Its output at the time step t denoted by YT is also a function of this. Okay, and the current input. Okay, so in case of the basic cell, as I have shown you, the HT and the YT are pretty much the same. Okay, the hidden state and the output are the same. But in a later discussion, when we talk about more complicated cell structure, okay, these two things may be different. So this is a more general situation. Okay, the input is X, the output is Y, and we have a hidden state H as a feedback. So it's going to be, when we unroll this through time, it's going to be something like that. Okay, and in a basic RNN cell, the Y and the H are the same, but it is not necessarily the case for more complicated cell types. Okay. So, an RNN can simultaneously take a sequence of input and produce a sequence of output. Okay. So here we are talking about 4 most commonly used RNN architectures. Okay, something like this. The first one is called sequence to sequence. The second type is called sequence to vector. The third type is called vector to sequence. The fourth type is called encoder-decoder architecture. Okay, so here we are going to talk about these 4 types. Okay, and their common applications. Okay, for example, the sequence to sequence, okay, is normally used for predicting time series. For example, it can be used to predict stock prices. So you feed it the prices over last n days, okay, and it will output the price shifted by 1 day into the future. So from n-1 day to tomorrow. Okay, so this is what's going to happen. Okay, so this sequence to sequence, okay, we are going to revisit this sequence to sequence architecture, okay, in the example, okay, in the example. So alternatively, okay, you could feed the network a sequence of input and ignore all output except for the last one. Okay, this is sequence to vector. Okay, sequence to vector. So you could feed the network a sequence of words, corresponding to a movie review, okay, sequence of words corresponding to a movie review is considered as a sequence, okay, and the network would output a sentiment score, okay, basically to represent like a, is this review positive or negative? Okay, positive means +1 means the review loves this movie. Reviewer loves this movie. -1 means the reviewer hates this movie. Okay, so this can be output by that single output. Okay, so this is the sequence to vector, and we can also have a vector to sequence. Vector to sequence. Okay, you can feed the network a single input at the first time step. Okay, and zeros for all other time steps, and let it output a sequence. Okay, so this is a vector to sequence network. Okay, for example, the input could be an image, and the output could be a caption for that image. The caption obviously is some description, right, of words. So I mean, description of words, I mean, is considered like a sequence. Okay. So last one. Okay, you could have a sequence to vector network. Okay, this sequence to vector network is called the encoder. This one. This one. This part we call it encoder. So this is pretty much a sequence to vector. Okay, and then you have a vector to sequence. We call that decoder. Okay, so this is like this structure is a lot of time used for language translation. Okay, so the input is a sequence, the output is also a sequence. So you may ask, well, so since the input and output are both sequences, why don't we just use the first type? Sorry. What's the difference between this one and this one? Okay. Let me first explain, okay, how the translation happens. Okay. Basically here, okay, obviously you feed like a word in a sentence. Okay, maybe in English. Okay, and that whole sentence will become an embedding. Remember, I explained the concept of embedding to you guys earlier, right? So it's kind of like a lower dimensional vector representing like the meaning of that sentence. Okay, so it passed that vector to this decoder, and this decoder will then translate like into another language. For example, maybe Chinese. Okay, something like that. Okay, so the difference between this one and that one is in the sense that, okay, because in a whole sentence, I mean, the last few words may have big impact to the meaning of the whole sentence, right? Right? For example, like in English, if I say, can I have some example? For example, like if I say, can I go to the movie? Probably not. Okay. Okay. For example, let's say, shall we go to the movie? Let's go to the movie, right? Okay. If I add like a last word, okay, then I'm asking, right? I'm asking you, okay, we want to go to the movie or not, right? But without that right or okay, the last word, let's go to the movie. It's a passive sentence, right? It is not a question sentence, right? It's not asking, okay? So you can see this example, okay? The last few words may have a big impact to the to the meaning of the whole sentence. So in this situation, you are able to, consider all the input of every words in the sentence and put that into an embedding, and then be able to translate the sentence, okay, with the consideration of every single word in the sentence. But in here, okay, if you are doing like a shall we go to a movie, okay, then because this input, okay, is going to only impact this part. The previous part, there's no way this input is going to be fed to the previous recurrent neurons. So this input cannot be used to have any inference to the previous translations. In many language, okay, this may produce incorrect translations. Okay, so that's the issue. Okay, so that is why this architecture is more often used for language translation. Okay. So you guys know we have sequence to sequence, sequence to vector, vector to sequence, and encoder-decoder architecture. That is, those four types are the most commonly RNN architecture. Okay, so how do we train an RNN? Okay, to train RNN, okay, we are going to unroll it through time. Okay, and then simply use a regular backpropagation. Okay, so this strategy is called backpropagation through time, BPTT. So it's going to be something like this. Okay, so this is like this is actually an RNN network. Okay, but with a weight and a bias. Okay, and because we unroll it through time, so you can see like we have all these. But sometimes we only consider, for example, the last few inputs. For example, Y2, Y3, and Y4. Okay, we have like the ground truth of this, and then we do the comparison, and then it's able to calculate the error. Okay, and those errors will be considered as a gradient that's flow back through this direction, and this arrow, this gradient flow back is also going to flow back to, through this unroll through time stuff. Okay, but these two, okay, these two outputs, they are not, okay, if they are not used in a cost function, then pretty much we don't consider them. Okay, there's no gradient flow back in here. Okay, so based on this, one thing you can learn, okay, is that, okay, when you train the RNN, okay, there are two considerations, because in the previous cases, when you train MLP or CNN, okay, most of the time, like the only matter is the layer, right? The more layer you have, or each layer, if you have more neurons, then how should I say? The training becomes more difficult. You may need more memory. You may take more time to train. But in an RNN, okay, the number of neurons in a layer as well as number of layers still matters. But one more factor to consider is how many, time steps do you need to consider, okay, when you do this unroll through time. during training. So the time step, okay, to expand is also one factor to consider. This add like one additional complexity when you train an RNN model. Okay? Just want you to be aware of that. Okay? So let's take a 10 minutes break. When we come back, we will continue the discussion. We are going to talk about an example of RNN network. Okay?